Magnetic properties of materials. The discussion in the previous section helps us to qualify materials as diamagnetic, paramagnetic, and ferromagnetic. In terms of the susceptibility, a material is diamagnetic if its susceptibility is negative, paramagnetic if its susceptibility is positive and small, and ferromagnetic if its susceptibility is large and positive. Diamagnetism. Diamagnetic substances are those which have the tendency to move from stronger to the weaker part of the external magnetic field. In other words, unlike the way a magnet attracts metals like iron, it would repel a diamagnetic substance. Figure shows a bar of diamagnetic material placed in an external magnetic field. The field lines are repelled or expelled and the field inside the material is reduced. Diamagnetic substances are the ones in which the resultant magnetic moment in an atom is zero. When magnetic field is applied, those electrons having orbital magnetic moment in the same direction slow down and those in the opposite direction speed up. This happens due to induced current in accordance with the Lenz's law, which you will study in the chapter Electromagnetic Induction. Thus, the substance develops a net magnetic moment in a direction opposite to that of the applied field and hence repulsion. Some diamagnetic materials are bismuth, copper, lead, and silicon. The most exotic diamagnetic materials are superconductors. These are metals cooled to very low temperatures which exhibits both perfect conductivity and perfect diamagnetism. Here the field lines are completely expelled, that is susceptibility is equal to -1 and mu r is equal to 0. A superconductor repels a magnet and is repelled by the magnet. The phenomenon of perfect diamagnetism in superconductors is called the Meissner effect. Paramagnetism. Paramagnetic substances are those which get weakly magnetized when placed in an external magnetic field. They have tendency to move from a region of weak magnetic field to strong magnetic field, that is, they get weakly attracted to a magnet. The individual atoms or ions or molecules of a paramagnetic material possess a permanent magnetic dipole moment of their own. On account of the ceaseless random thermal motion of the atoms, no net magnetization is seen. In the presence of an external field B0 which is strong enough and at low temperatures, the individual atomic dipole moment can be made to align and point in the same direction as B0. Some paramagnetic materials are aluminium, sodium, calcium, oxygen at STP and copper chloride. Magnetization of a paramagnetic material is inversely proportional to the absolute temperature T, or we can say M is equal to C into B0 by T. Susceptibility is equal to C into mu naught by T. This is known as Curie's law. Note, for a paramagnetic material, both susceptibility and mu r depend not only on the material but also on the sample temperature. As the field is increased or the temperature is lowered, the magnetization increases until it reaches the saturation value Ms, at which point all the dipoles are perfectly aligned with the field. Concepts. What are different types of magnetic materials? Solution: diamagnetic, paramagnetic, and ferromagnetic. What is the sign of susceptibility of diamagnetic materials? Solution: it is negative. Number 3. What is the Meissner effect? Solution: a superconductor, when cooled to a very low temperature, repels a magnet and is repelled by the magnet. This is called Meissner effect. Number 4. What is Curie's law? Solution: magnetization of a paramagnetic material is inversely proportional to the absolute temperature T. This is the Curie's law. Ferromagnetism. Ferromagnetic substances are those which get strongly magnetized when placed in an external magnetic field. They have strong tendency to move from a region of weak magnetic field to strong magnetic field. That is, they get strongly attracted to a magnet. The individual atoms or ions or molecules in a ferromagnetic material possess a dipole moment as in a paramagnetic material. However, they interact with one another in such a way that they spontaneously align themselves in a common direction over a macroscopic volume called domain. When we apply an external magnetic field B0, the domains orient themselves in the direction of B0 and simultaneously the domain oriented in the direction grows in size. This existence of domains and their motion in B0 are not speculations. In a ferromagnetic material, the field lines are highly concentrated. In non-uniform magnetic field, the sample tends to move towards the region of high field. We may wonder as to what happens when the external field is removed. In some ferromagnetic materials, the magnetization persists. Such materials are called hard magnetic materials or hard ferromagnets. Alnico, an alloy of iron, aluminium, nickel, cobalt and copper, is one such material. On the other hand, there is a class of ferromagnetic materials in which the magnetization disappears on removal of the external field. Soft iron is one such material. Appropriately enough, such materials are called soft ferromagnetic materials. Note, the ferromagnetic property depends on temperature. At high enough temperature, a ferromagnet becomes a paramagnet. The domain structure disintegrates with temperature. The temperature of transition from ferromagnetic to paramagnetism is called the Curie temperature and is denoted by Tc. The susceptibility above the Curie temperature, that is in the paramagnetic phase, is described by C divided by T minus Tc, where T is greater than Tc. Now the Curie temperatures of some ferromagnetic materials are as shown in the table. The relation between B and H in ferromagnetic materials is complex. It is often not linear and it depends on the magnetic history of the sample. The magnetic hysteresis loop is the BH curve for ferromagnetic materials. Let the material be unmagnetized initially. We place it in a solenoid and increase the current through the solenoid. The magnetic field B in the material rises and saturates as depicted in the curve OA. Next, we decrease h and reduce it to 0. At h equal to 0, b is not equal to 0. This is represented by the curve AB. The value of b at h equal to 0 is called retentivity or remanence. Next, the current in the solenoid is reversed and slowly increased. Certain domains are flipped until the net field inside stands nullified. This is represented by the curve BC. The value of H at C is called coercivity. As the reversed current is increased in magnitude, we once again obtain saturation. The curve CD depicts this. Next, the current is reduced, curve DE, and reversed, curve EA. The cycle repeats itself. Note that the curve OA does not retrace itself as H is reduced. For a given value of H, B is not unique but depends on previous history of the sample. This phenomenon is called hysteresis. The word hysteresis means lagging behind and not history.